friends, welcome back to another video from our Machine Learning with Python tutorial, where we explain different machine learning algorithms. We go over the math behind it and then implement it in Python from scratch so that you have a better understanding, like a very clear understanding of what is exactly going on, and that hopefully helps you learn better. In the previous videos, we talked about the k-nearest neighbor model, and we also discussed the linear regression models. We implemented both algorithms in Python from scratch, and we saw that the behavior of the classes that we implemented perfectly matches those from, Python's scikit-Learn library, and we did good. In today's video, I want to talk about the naive Bayes. What is naive Bayes? That's another machine learning algorithm, which is used mostly for classification tasks. And today, let's say the problem that we want to solve is that we want to look at someone's health measures, as you can see here, like the BMI and the protein level and stuff like that. And based on that, we want to say if that person does yoga or not. Okay, cool. So I can just go over the math behind it and explain what's happening there, but I thought it'd be, easier if I give you an example so you can actually see what's going on. So let's say that we have a database of 20 people, right? These are the 20 people that we have, and some of them are fit, some of them are not, right? And we measure body mass index, the BMI, and the protein level for each person. And then we have a database of the BMI and protein level of people who do yoga and those who don't, right? And the question is, when you're giving a new person, and let's say you have the BMI and the protein level of a new candidate, can you tell if that person does yoga or not? The math is given here, right? Up here. So basically what it says is that the probability of someone does yoga or doesn't yoga, Y could be any class, given x1, x2, x3, and so on and so forth, and xi's are basically the input features. In this case, we have only two features, the BMI and protein level. That equals probability of, x1 to xj, given that that person does yoga or doesn't yoga, depending on what's y, times probability of y, and divided by px1, all the way to xj. So what this algorithm does is basically calculate these equations for each of the classes that you have. In this example, we have two classes, people who do yoga and people who don't do yoga, right? We can make it more complicated, people who do yoga more than 3 times a week, people who never do yoga, and people who actually do yoga, I don't know, maybe once or twice a week. And for each of those classes, you have to calculate this probability, right? In this case, you only have 2. So you calculate both, and then you pick the higher probability and say, okay, because based on the input features that I had, this person is more likely to do or not to do yoga. This is basically what's happening. Because we are calculating these equations on this slide on the right, I should probably be able to do this and come here and say, because we are calculating this, and it's the sound, and if you look at this part in here, it would be the same for each class. For if y is do yoga or don't do yoga, this part, regardless, is the same. So we remove that part from our calculation to make it easier. And we are more interested in this part only, right? P of x1, x2, xj, given, if the person does or doesn't do yoga, multiplied by py. And the other assumption that we are making here is that the input features that you have, x1, x2, and so on and so forth, are independent features, right? For example, if you have BMI here and protein level, let's say I don't really know much about health, but let's say they're independent, right? if instead of protein you had like a function of BMI, like BMI times 2, right? That's like not really an input feature because that doesn't really give you any new information. So yeah, this is an assumption that you have to be aware of, and that's the fact that the input features are independent. So if that's the case, the probability of x1 and x2 and xj given py, that's basically, because they are independent, is px1 given y times px2 given y times, and so on and so forth. So I can rewrite this equation as y given, and instead of x1, x2, xj, I'm just going to go capital X. That equals p x1 given y, right, times p x2 given y. And we're just talking for this example, we have only 2 features, so I'm just gonna stop here and go py, right? This is a bracket. So this is what we want to calculate: probability of the BMI given that person. Let's say y is if person does yoga, right? We want to say like probability of the BMI if that person does yoga, and multiply it by the probability of the protein level of that person doing yoga times the probability of that person doing yoga, which is coming from this data set in here. Let's say that 12 out of the 20 sample, I have 20 samples here, right? So 12 out of 20 here, and that's like 60%, right? 0.6. So this is probability of doing yoga, say yoga. And here I only have like 8 people, right? I'm just gonna go 8 over 20. Then that's like 40% of, and I'm just saying not do yoga, for example. And this is py. So if you're calculating the probability of a person doing yoga, then you put 0.6 in this example here. And if not, you put 0.4. So that's about it. But the main question is, okay, how do we calculate px1 given y has already happened and px2 given y has already happened? So to do that, we actually, this is why it's usually called the Gaussian naivebayes algorithm, because like we're using Gaussian distribution, right? So we say that, let me go to the next slide so there is more room. We're going to say that for the people who do yoga, I measured BMI, and I'm assuming that like BMI is like having a normal or a Gaussian distribution or something. And it's something like this, for example. And I measured the same thing for the protein level, and that's like this as an example, right? And this is for like yoga. And then for people who don't, I measured it, and I noticed that like this is the PDF actually. This is not the BMI level. And then I noticed that it's like something like this, the BMI, and it's just like BMI, and that's the PDF, the probability density function. That's the same thing for here. And for the protein level, let's say it's like a different distribution. It's like this. And so this is how we measure those 2 probabilities here, right? These 2 probability. Let's say a new person comes in, right? And it says the BMI of the new person, I'm just going to go new person, oops, what's happening here? I'm just going to go here and say BMI for that person is like 25, and the protein level, that's like, I don't know, 30, for example, right? So what you're going to do is that when you're doing this for, let's say that person does yoga, you use these 2, these 2 plots in here. And if you were calculating for a person that doesn't do that, you use these two plots and you say, okay, like I have this distribution, I have the mean, because like the mean value and the variance are the only variable that you need to define your Gaussian distribution. And you get those values from your sample data, right? Like if you go here, you have your sample data, you say, okay, I measured the BMI of the people who actually do yoga, and the mean is that based on this table in here, and the variance is this, and same thing for the other feature. That's how you come up with these plots and with these PDFs, right? And then now that you have the distribution, you just put these values like 25 and 30 in this example to these two plots respectively, and you get a probability. And once you have the probability, everything else is just simple. You just like multiply it. The other thing that you need to notice is that because sometimes these probabilities are very small, right? And like tiny values. And it makes it sometimes really hard to work with these values. That's why in most cases, people actually like calculate the logarithm of these values, right? Because like, for example, if you have, I don't know, let's say that you have a value and that's like 0.0 this, if you get the log, it's going to be like -3 if like in base 10. Like like 10 of that number would be -3. So if this number is like very tiny, then some computers just simply do not have enough precision to show that number and they would return 0. But this is not actually 0. That's why you take and calculate the log to like deal with some, more reasonable values. And obviously when you calculate the log, all these multiplications here are like converted into addition. So that would be px1 given y plus px2 given y plus py. And so, yeah, that's the only thing that you need to keep in mind. So I think that's it about the math behind it and the explanation of the algorithm. Now let's move to Python and see how we can implement it there. Let's open Visual Studio Code. As always, I'm just gonna import NumPy as in P. I'm also gonna, because we want to compare it with the scikit-learn method, I'm just gonna import scikit-learn, and well, not the whole thing. I'm just gonna go from scikit-learn, right? Import data sets, because I want to like bring a data set over from, again, scikit-learn dot naivebayes import. What are we importing? Gaussian naivebayes. And also from scikit-learn model selection. You already know this. Import train test split, right? These are the libraries that we're going to need. And just for the sake of being able to reproduce the results, I'm just going to go numpy.random.seed. Just set the seed to 0 or something. Okay, now let's start coding. I'm just going to go x and y. That equals datasets dot. Just going to go load iris. We've worked with this data set before. So we know that like there's 3 classes in that data set and with 4 features, if you remember. If not, just like Google datasets, like iris dataset, and you'll see the data set. So return xy is true. I want to read the data set and get all the values back and save them in x and y. And so yeah, just to make sure that we're doing the right thing, I'm just gonna go print x.shape, right? And if I run that, it's not it's not comma, it's dot. Okay, and if we print that, it says we have 150 samples, right? Like the first the first argument, the first part would be the number of samples, which is 150. And then like we have 4 features. And if you remember from these 150, like 50 are from one class, another 50 from the second class, and the last 50 from the other class. Anyway, so we load the data set and we do the same thing, xtrain, xtest, ytrain, and ytest, that equals train test split, and xy, and I'm just gonna go test size equals 0.2. You can play with that if you wanted to. And now actually let's use the scikit-learn model. So I'm just gonna go gaussian naivebayes, create an object. It's gonna be gaussian naivebayes, right? And gmb.fit. What can we do? Xtrain, not the test because we're training, xtrain and ytrain. So it gets the training inputs, like the input features and the training labels and model. It trains the model, and then we can go ypred. The predicted values are going to be gnb dot predict, and you want to run that on your x test values. And then we can say print, for example, what do we want to print? We want to say mislabeled. How many labels? I'm just going to go ytest. If ytest is not equal to ypred, sum that, right? And this is like the number of mislabeled inputs. So mislabeled this many samples out of how many samples do we have? That's obviously length of the test, the x test, which we can do it like x test dot shape, and as we said, like the first argument is that. So we're gonna do this. Oh, it's here in Python. I don't know why. And let's just clear this, and let's run this and see what we get here. Okay, so it says mislabeled 1 sample out of 30. We can just like make it pretty and like with a bracket in here. So it's like 1 sample, not 1 samples. So it's about, how you use the scikit-learn model, which is like super easy. And now it's time to write our own class, right? How can we do that? Let's get started. I want to define a class, and I'm just going to call that my own naivebayes. And define, we can't define the init, but like honestly, you don't really have to. Like in all the previous examples that I've done, I've been using the init class. But in this example, I don't really want to use that, so that you see it works without the init. The init method, sorry, I was saying class, without the init method. So I'm just going to define the fit method here. Well, it obviously, the fit method, it's going to need x values and y values so that like it can does the training on that. So what's going to happen is that I'm going to get the I want to get the features and the number of samples because I don't know what I'm dealing with. So I'm just going to go number of samples and number of features, for example, that equals x the shape, right? So I get the x shape, right? And then I don't really know how many classes I have, right? Because like it's important, because when it comes to, having these graphs, like we have to calculate and like the mean and the variance of each of these features for each of the classes, right? So in this example, we had 2 classes and 2 features. That's why we have like 2 sets of these, diagrams. And in each set because we have 2 features, we have like 1 plot for each feature. That's why it matters, right? So we need to know the number of classes. So I'm just going to go self dot. I'm just going to use underscore because it's not a method. It's like a variable. I'm just going to go classes. So like that's all the classes that I have. I don't really know the classes, the labels. I just want to know, like, get all the classes, put them into this variable, and then I can be able to say number of classes, for example. That would be length of self dot underscore classes, something like that. But how do I know like how many classes I have? NumPy gives you this cool option. You can just go NumPy dot unique, NumPy dot unique of y. So if you have a NumPy array and you call this function on it, what happens is that, let's say your array is like, let's say you have something like, I don't know, 1, 2, 2, 3, 1, and then after you call this, you're gonna get 1, 2, 3, right? It's not gonna, like, it sees that, okay, you have like 2 occurrences of 2, and it's just gonna ignore that. It just like returns the unique values, right? That's what, like, it's gonna be 1, 2, 3, and then like here in this line, when you call the length function, it says, okay, I have like 3 classes, something like that. So that's about that. And as we said, we need to define those PDFs, right? The plots that I showed you in here, right? Now we need these. So we need the mean and the variance for each of these, right? Okay, how can we do that? I'm just gonna go self dot underscore average, right? It's a NumPy of zeros. And what's this? I just want to initialize them here to all zeros. I just want to go, it's like number of classes, right? In that example, we had 2 classes. So it's 2 by each feature needs its own plot. So number of features as well. And the other thing that you need to think about is that when you're calling this, when you need to initialize like an array of zeros, you have to define data type, right, in NumPy, because it doesn't know, like, if like it's a integer 0, it's like a float value, what is it? So I'm just gonna go data type, right, that equals NumPy dot float 64, for example. And I want to do the same for, let's say, the variance, because like for each plot we need the mean, or like they called it average here, and the variance, and that's going to be the exact same thing. We're setting it to zeros, and we need something else. Let me go back here. So you saw, for example, in this example we had py. For each class we need to calculate these because it's important, like it comes in the equation, right? This is called the prior probability because it's like prior to any calculations, and it's just like from the database. And this is called prior probability. Anyway, so we're going to calculate that as well. So I'm just going to go self dot priors, for example, that equals NumPy the zeros. How many do I want? I want number of classes, right? And then I'm just going to go data type equals NumPy the float 64. So we have them, and now it's time to actually calculate them, right? Like here, I set them on I initialize them to all zeros, and now we want to calculate it. I want to go for, and I want to loop through all the classes, right? So I'm just going to say for C in self dot underscore classes. So for each class, self dot underscore, oops, I forgot to add the underscore here. It's prior underscore priors. Okay, we need a loop index because like we set it to 0. So let's actually do it this way: idx nc in enumerate, of that. So now I'm just gonna go self dot underscore priors of index, right? That would be, let's actually define something else here as well. I'm just gonna go xc, like x of that specific class, because like you have in this example 150 samples, right? And it's just, I'm interested in the rows that belong to a certain class. So I'm just gonna go xc, like the input value, input features of this class, which I'm iterating to over. It's gonna be x var y, the given label, equals c, right? And that's the c. So it looks in the classes, because we're training supervised learning model, right? It looks at the labels and says, okay, if that's the case that I'm iterating over, then I need the input features for that. So in that case, I'm just gonna go here. It's gonna be xc. I don't know what I did, but xc the shape 0. I'm just gonna get the total number, right? Because this gives me the number of samples, if you remember, divided by number of samples that we have. So that gives me the prior probabilities for each class. I also need to calculate the average and variance for each class and for each feature. So I'm just gonna go self dot underscore avg, or average, of idx, right? And whatever column that is, like it, like all the columns, right? Because like in this example, we have 4 features. So it says for that class, and you know, all the 4 features that you have, do what? I'm just gonna go xc, which is our sample. It's a NumPy array, so I'm just gonna call the mean function from NumPy, and I'm just gonna go axis equals 0. So it means that like calculate the mean value for this over axis 0. If you don't know what that means, you can like honestly just look up the mean function for NumPy array, but it says basically calculate the mean over the x-axis. So like it gets all the y values, you know, all the row values, and like calculate the mean. And you can do the same thing for variances, but instead of mean, you're just gonna call the var function, and this is going to be var again. And this is how we calculate, you know, the average, the variance, and the prior probability for each class. So this is about our fit method. What else do we need? We obviously need a predict model method. So I'm just gonna go define predict, right? It gets self because it's part of the class, and x, which in this case would be the test values. Let's close this. And then actually let me do something. Like if you remember in one of the videos, we said the same thing. We said like let have a helper method that calculates the probability for each sample in X. And then here we can just keep calling that helper function. So let's go pass for now here. And then we can go underscore predict. Again, like we've done this before, you've seen it itself. And I'm just gonna give it small x. So it's just like one sample in X, which in this case would be text vector. So for each value, I'm gonna define probabilities, right? And set it to like an empty list. And I'm gonna go for, we are gonna have the same loop as we had in the fit, because we want to like loop through all the classes and all the features and everything. So we're gonna have the exact same loop, idx and s and c, in enumerate of self dot underscore classes. So for each of these, I'm gonna go, I want to calculate the prior. Prior would be NumPy, because like if you remember, he said like let's calculate the log so that we can like deal easier with the small numbers or like huge numbers if we ever got them. So NumPy the log of what do we want? Self dot underscore priors, right? We calculate it in the fit, and now here you're calculating the log of that and IDX, obviously. So we have that. And now we have to calculate the probability of each feature within that class, and like the mean values, and like add all those probabilities. So probability would be NumPy dot. We need a sum because we need to add all like the probability of all the features. So sum of what? NumPy dot log of what? Self dot and that's like the actual probability, right? We haven't calculated the probability yet. We have the mean value, we have the variance, but we don't have the probability. So I'm just gonna go underscore PDF, probability density function of IDX, right, and X. And then we have to define the PDF. So let's say that let's assume that we have the PDF. I'm just gonna define it in a second. But assume that we have it, let's complete these now. And now that we have this, the next step, like if I go back to the slides, you will see it's like probability of x1 given y after we get the log plus probability of this, which is like sum of all the features, probability of all the features, which is what we did here, and that plus log of py, which is what we did up here. So we need to add them. So I'm just gonna go prob equals prob, what we calculated up here, plus this guy, right? And probs, which is this list, just gonna append it to that. So it's just append that to like append prob to that list. So probs at the end of the day would be the probability of each of the classes, right? What we need though is to calculate the highest number in that list, right? I mean, like, okay, like this is probably the class that fits better. NumPy gives you an option, like you can basically like have a for loop, go over all of that and like calculate the max and stuff like that. But what it does it for you, NumPy does it for you. So I'm just gonna go return self dot underscore classes, and here I can go NumPy dot argmax of props, right? It does the job for you. Now we need to define the PDF function. This is what we missed, and then we also need to like finish the predict method in there as well. So let's define the PDF. It's super easy. We have the mean values, we have the variances. The PDF is just basically the implementation of the Gaussian distribution. So I'm just gonna go underscore PDF. I call it underscore because it's like a helper function. I call it per method for that matter. Self, and I'm gonna get the class. I'm getting the class IDs as well, right? Because like we need to calculate that for each of the classes. And obviously we need the X value because we want to return a probability, right? So that like a new sample comes in. If I go back here again, a new sample comes in and it says, for example, the X is this, like BMI is, for example, here, and it's this, and the protein level is here. So you want to calculate the corresponding Y to these values, right? So you need the input X. And basically you can go average equals self dot underscore average of that class, right? So you're just going to put class ID X. So you have the average here, and you can do the same thing for the variance. So if I go more here and then more here, that's and then Gaussian value, or the PDF, or whatever you want to call that. I'm just going to say Gaussian PDF or whatever. That equals, here you just want to implement the Gaussian distribution, right? So if you know that, it's going to be exponential of what is it? So it's going to be, I think it's going to be X minus the average value, right? That you need to square that. And once that's done, you divide that by 2 times 4, I think. And then the whole thing needs to be divided by numpy.sqrt, which is the square root of 2 times variance times numpy.py, which is like the 3.14. So this is just basically the definition of the Gaussian distribution with a given mean and variance. And once you calculate that, you can just like return the GPDF. So we have a helper function. Let's go back to predict one more time before then. So here we get the X value, and then we calculate the probability for the given class for that X. And so this is the PDF. And then here the X value comes in. We calculate the prior probability of that class, and then sum of all the features, and then like add them all together and return all the probabilities, and like we calculate the maximum probability because that would be the answer. And now that we have this, we can go back here, and then we can say ypred would be, if you remember, we've done this before, the self._predict of X, right? For X in X, right? And then we can simply return. We have to convert it because like this is going to be just a list, but everything else is in a NumPy array format. So we have to convert that into NumPy array of ypred. So return that. So this should be our class. I think we covered everything. Let's just, we are here, and make this smaller so that you can actually see the code better. Yeah, so we have the class here. I don't think I've missed anything, but I guess we'll see. Now let's actually use our own class. Now I'm just gonna go gnb equals my naivebayes and gnb.fit. It's gonna be the same step, so that's going to be train using xtrain and the train labels, which is the ytrain, and then ypred, that would be gnb.predict x test, right? You give it test values and then they calculate it, and we can just like bring the error message here as well. Just put it down here. And so if I run that now, well, mislabeled using this for our own naivebayes, and then here this would be for scikit-learn naivebayes, right? So if I run that, hopefully we get the same thing. Okay, so we're getting an error here. In the fit function, it says missing one required argument in line 47. So what's going on? Oh, yeah, I forgot to define, like I forgot to add the brackets in here. So you add the brackets here, and then hopefully that fixes the problem. That was an interesting mistake. I was confused with that. So let's just run this now. And it says, yeah, mislabeled 1 samples out of 30 for that, and all of the samples were there. I don't know what's going on here. Let's see. So we made a mistake here. Like when we defined, this is like what we're not getting the same values. So numpy.exp, we missed a minus signing here. So the plots, the PDFs that we were calculating were completely wrong. So let's just clear that and run that again. And yeah, and now we can see that it exactly matches. Mislabeled 1 samples out of 30. If you think it's by accident, like you can play with these values here. Be like, hey, I want like less data for training, more for testing. So it just reduces the accuracy of your models. So let's say I just want to go like 40%, right? And if I run that now, I see I get like 40 samples out of like 60, because like now I have more sample data, but like samples are failing. If you want, you can write a piece of code that actually tells you which samples are failing, right? And if I increase that, like be like, I want like, I don't know, 60% for testing and 40% for training, which is obviously not a reasonable thing to do, but just for the sake of testing, we can see that like 5 samples are failing. Anyway, that's it about the naive Bayes algorithm. Hopefully that helps you. And thank you again for watching me. And don't forget to subscribe so you won't miss the next videos when I upload it. And also it helps me. And you guys have a good one. Take care. See you in the next video. Bye-bye.